7, 6, 5, 4, 3, 2, 1. Go. We're live. This is Retraice, segment number 58 for Tuesday, November 22nd, 2022 at 11 p.m., 8 p.m. Pacific. What is Retraice? Retraice is about what's going on out there. The short answer to that question is computer control. Sometimes we use the term AI, but that's not really the right term. Other things that are going on out there are nature, which is not effing around, artificial intelligence, which is new, natural intelligence, which is old, strategic intelligence, by which we mean espionage, counterespionage, and covert action, which is in between, and humanity, which is the best part. And Retraice I'm screwing up my shtick. Retraice is for outsiders. But we came to the conclusion that outsiders are not players, and the computer control game is player-oriented, so now we're learning to play. I have to write all that stuff down because we've done a lot here. This is segment number 58. I can't land the plane without a checklist manifesto. All right. We're talking today about thinking and uncertainty. We're working on AIMA4e, Artificial Intelligence, a Modern Approach, the book, the brick, the one and only. Yesterday we talked about problem solving and intelligence and artificial intelligence definitions in general. Those were sections 1 and 2 of AIMA4e. Today we're going to be talking about sections 3 and 4. Yesterday I thought I was going to be able to do the rest of the book, but business side of the business took priority, and I lost 5 hours of time that I was supposed to give to this, so it's okay. It doesn't matter. If I had done the whole book, if I had done the whole rest of the book, which is like 75% of it or 80% of what I hadn't yet covered as of yesterday, this would be a long episode of the podcast, but it's still going to be long, but it's not going to be that long. It's not going to be long. See, I keep doing that. I keep anticipating. I don't know how long it's going to be. I haven't done it yet. Here we go. Just to review anything, I don't know. We talked, the first 6 chapters were yesterday. Those are the 2 sections, intelligence and solving. Those are our nouns for those sections. These 3 and 4, sections 3 and 4 are thinking and uncertainty. And then tomorrow we're going to do sections 5, 6, and 7, which are learning, interacting, and conclusions. So we're in the middle part of the book here, the middle part. And including section 4, which is uncertainty, which is the big one. That's the one. And it's dominated by chapters 13 and 18. And we'll talk about those in a second and why they're so dominating. All right, let's get to it. Chapter 12, quantifying uncertainty. So section 4 is about uncertainty. No, I'm jumping ahead. Section 3. Section 3, chapter 7, begins with chapter 7. Section 3 is about thinking, which they term knowledge, reasoning, and planning. I call it thinking. Chapter 7, 8, 9, and 10, and 11. You don't understand. This thing is a beast, okay? And to get it all into your head, you really have to take on a lot. It's 1,000 pages, and it's a lot. Oh, I'm just making excuses. All right. Chapter 7, logical agents. This is about forming representations and reasoning before acting. Representation is the thing that keeps coming up again and again in artificial intelligence if you start delving into the heavy stuff, which we've done a little bit here. You'll certainly do in your future. I'm sure you'll be forced to. You'll hear these things. I think are going to become common knowledge in culture eventually because they are so transformative in the way we think about things. But when we talk about representations, we're talking about how to represent the world or knowledge about the world inside of the agent. So knowledge representations are about how do you represent the stuff that's out there using whatever means, whatever formal language or however you're doing it, inside of your agent. And so as you hear that, when you hear that term representation, you should be thinking about it's basically world models. Okay, so chapter 7 is about knowledge-based agents representing the world, representing different worlds, logic, world models. Make you think of anything? Any podcasters out there talking a lot about world models and possible worlds? We're doing all of this in not first order logic, but what's the thing? Oh, crikey. Propositional logic. I'm sorry. So we're doing logic without objects, and we're talking about possible worlds. That gets important later on.
moving on from Chapter 7 to Chapter 8, first-order logic means now we have a formal language with which we can incorporate objects and relations. That's the difference between propositional logic, where you just have statements or propositions, and first-order logic, where you can deal with objects in the world and relations among those things. Sounds kind of important. You definitely are more of a first-order logic entity than a propositional logic entity. What it really comes down to is what they call ontological commitment. In philosophy, ontology is just the study of what exists. You usually think of ontology and epistemology. You can add a third category, but just don't for now. Ontology is what exists. Epistemology is what can be known. Okay, so when we talk about ontological commitment, we're talking about our formal language, which now is first-order logic, which admits of objects and relations. Propositional logic didn't do that, okay? They talk about the syntax and semantics of first-order logic, and knowledge engineering, i.e. building formal representations of important objects and relations in a domain. Important is a key word there. We're going to come back to that in a second. You don't just try and represent everything. You quickly short-circuit the whole system unless you have some sort of criteria for importance. Some things are more important than others. Again, sound like any podcasters in your life? I'm telling you, man, just Chapter 7 and 8. Like, I've glanced through these things, but it's just lining up so much with both the things that seemed to emerge from the first 50 or so Retraice segments as structures and objects of importance, and also the problems to which they led us, these sort of intractable, it's too complicated, or we don't have enough people, or blah, blah, blah sort of problems with finding out what's going on out there. Artificial intelligence, as compiled into a unitary body of knowledge by Russell and Norvig, seems to be working on the same sort of stuff a lot, or all the time. Only difference being just more of a formal and engineering approach, as opposed to what we were doing, which is more like English language reflection. Continuing on. Chapter 9, we're still in the thinking section here. First order inference. So we're talking about reasoning about objects and their relations. So algorithms to answer any first order logic question. That's what they offer in Chapter 9. Kind of nice. If you can formulate a question in first order logic, then we have algorithms that can answer it. Not necessarily efficiently, but that's kind of a powerful thing. Chapter 10, knowledge representation. Now we're back to representation. Representing the real world for the purpose or purposes of problem solving. And the basic question that Russell and Norvig put to us is, what content do we put into the knowledge base? It's one thing to talk about how it should be structured or organized, or what language you're going to use for your knowledge base, but then what do you put in it? Propositional logic has propositions. Just think statements or sentences. Propositions are sort of the abstract concept of statements or sentences. And then you got first order logic, which also adds objects and relations. Okay, great. So now we have our languages, but we don't put all the propositions into propositional logic. We don't put all the objects and relations into first order logic. That's where Chapter 10 comes in. Now, they do this great thing when they start talking about knowledge representation languages. In the beginning of the chapter, they mention different representation languages that they're going to use later. So I'm going to go through them. So first order logic is reasoning about the world of objects and relations. We've already talked about that. So that's one representation language, first order logic. Then there's hierarchical task networks is another representation language, and that's for reasoning about plans. You do that in Chapter 11. That's the next chapter. Bayesian networks. You might have heard of Bayesianism or Bayesian networks if you've dabbled in artificial intelligence. Though that representation language is for reasoning with uncertainty. And remember, uncertainty is the big section. That's the big middle section that's bigger than 50% bigger than all the other sections, all the other 6 sections of the book. Markov models, MARKOV models, are for reasoning over time. You can do a lot of reasoning without taking into account the linear and extended nature of time and its effects on your situation or your problem or the problem you're trying to solve or your solving of that problem. Deep neural networks are a knowledge representation language for reasoning about images, sounds, and other kinds of data. If you're sort of skimming the high level of artificial intelligence in our time, since basically 2012, and deep neural networks Was it 2012? It was about then, where they sort of exploded the image. Someone, Jeff Hinton, and then there was a lot of. It was always they were always working on it, but there were real breakthroughs in like 2008, 2012, and we started to be able to. They started to be able to recognize objects and images and do like a lot of textual feats of intelligence using deep neural networks, which I'm not going to go into what they are. I could give you a thumbnail sketch, but just put a pause on deep neural networks for now. We'll talk about those in learning tomorrow. Okay, that's Chapter 10, Knowledge Representation. Chapter 11, Automated Planning, Hierarchical Task Networks is what we just mentioned as the knowledge representation language. So we're talking about planning for spacecraft. You don't just launch it and hope, and you're not holding a joystick when you fly something into space these days. It's all programmed in advance. Planning for factories and military campaigns. We're talking about representing actions and states with our hierarchical task network, and we want efficient algorithms and heuristics. That's what's on offer in Chapter 11. That's the end of thinking, okay? So logical agents, first-order logic, first-order inference, knowledge representation, and automated planning. Those are the 5 chapters in the thinking section. Make sense? Okay. Remember, we started with intelligence in general. Then we talked about problem solving. That was Section 2. Section 3 we just talked about, which is thinking, which is more broadly knowledge, reasoning, and planning. Now we're going to talk about the big one, uncertainty. Uncertain knowledge and reasoning. I think they should have titled it Uncertain Knowledge, Reasoning, and Planning, because they do talk about planning just like they do. Would have just been adding the word uncertainty to the thinking title, which was Knowledge, Reasoning, and Planning. But anyway, it's uncertainty. That's why I just lopped off all the nonsense and just said uncertainty. This is a chapter, Section 4, which is chapters 12 through 18. So why is the uncertainty section big? It's because of chapters 13 and 18. They're much bigger than the other ones, and it has more chapters. Like the number of chapters in the book kind of goes up and then goes down, sort of a bell curve. But it's the number of chapters and also the size of chapters 13 and 18. What are chapters 13 and 18 about, you might ask? Well, 13 is about probabilistic reasoning, and 18 is about multi-agent decision making, which is a fancy way of talking about strategy and game theory in a world of competing and cooperating agents. Agents, right? You can think artificial intelligent agent, or you can think of strategic intelligent agent, right? Espionage, counter-espionage, and covert action. I'm telling you, I'm not doing this on purpose. It really lines up with what we've been talking about. It's almost like something. I'm telling you. All right. It's okay. It's all on record. I'm going to be calling back to old segments of Retraice for the rest of our study of this book, because they're just the fibers are woven together. Okay. So Section 4, uncertainty, starts with Chapter 12. Let's quantify uncertainty. We want to, and what we're going to come up with here, they come up with an answer to the thing that kills formal logic. Can you imagine what kills formal logic? It's your fault. It's because you're lazy and ignorant. Now, just pause for a second. No, those are not my words. Laziness and ignorance are the technical terms that they use for what kills formal logic. Pause for a second. Does that sound familiar to you? What did we say? The game is player-oriented. We said that people who are incapable and ignorant will be irrelevant and ignored. Okay, so there's just parallels and little echoes and things that shapes that resemble each other. So here's how laziness and ignorance kill formal logic and require us to find something new. So the causes of uncertainty in an environment are the environment types. Remember, going back to yesterday, we talked about the models of environments that Russell and Norvig offer, and there are a couple of good ones, and we won't go into the details, but breaking down all environments into 6 or 7 aspects, depending on what level of detail you want to deal with and what sort of capability you have in working in those environments. And by working, we always mean problem solving. That's all we're ever talking about in official technical artificial intelligence. Agents pursuing goals by solving problems. So the environment types that cause uncertainty are things like partial observability, okay? If you're familiar with the object constancy phenomenon in psychology, babies are not born with the ability to comprehend or retain that when they can't see something, it still exists in the world. And even and once they develop that ability, it's that object constancy ability, then they've passed some sort of developmental threshold. I don't know if it was Piaget. I don't remember who did it, but came up with that. But you also have an object constancy problem. What do we mean by that? Well, we spend a lot of time on uncertainty in Retraice, and we have spent a lot of time on trust. And what are we doing when we trust a source? Well, it could be any kind of source. It could be somebody you know, somebody in the mass media, blah, blah, blah. We can't go and see for ourselves. We're not talking about direct apperception. We're not dealing with things directly. We're not talking about trusting our senses so much as trusting the word of another person. But I think the way that we framed this early on was, what is it? Something in reports. Anyway, what is it? Something in reports. Oh crap! I forgot it. Anyway, it's in the early Retraice. I've already forgotten it. Partial observability creates uncertainty. Everything in your world is partially observable. You can't even see what's outside of this box in which you're watching me behave. What could be? You don't know what's over here. Look, my hand's already gone. It's out of the box. Where did it go? Well, you can't observe it. It's partially observable. There's some uncertainty. Maybe my hand is holding $1,000 in cash. Maybe my hand is holding a Tic Tac. Maybe it's holding nothing. You don't have certainty. See, you can see now, you can be almost certain, but really you're not watching my hand. You're watching a digital representation of the information that was once gathered by several machines and etc. Partial observability creates uncertainty. Non-deterministic environments where you can't know what's going to happen just because you know what's happening or what happened. And then adversarial environments cause uncertainty. Adversaries. We're going to get to that big chapter 18. That's where everybody's fighting and working together. Also makes you think about blue and red politics. Come on, people. It's all tied together. All right. Your belief state, your state, your belief state is, or the agent's belief state is the representation of the world, based on its percept sequence. And its agent function. So stupid. Like, that's such a terrible way to describe it. I'm out over my skis here. You got to understand. Like, this is the section where I'm not nearly as strong on this stuff as I am on the early stuff. But time will fix that. Time and effort. Okay, so your belief state grows big and unlikely very fast. If you're only using logic, if you're using straight propositional logic or even first order logic, we need some way of thinking about the world. In artificial intelligence, we already have it in our brains, but in the discipline of artificial intelligence, we need some way of thinking about the world that isn't composed of propositions. Okay, like you can't, and objects and relations, because if you start listing them, this is where the laziness comes in. It's too much work to list everything, and even if you do all the work to list every relevant proposition, every relevant object in relation to the in the domain where you're trying to reason, where you're trying to solve a problem, it's too much work to use the list. Even if you were not too lazy to build the list, it's too much work to use it. Ignorance is the other thing. There are no complete theories of anything in the world, so there are things that we don't know about every domain, and that's the theoretical side. And on the practical side, we can never run all the tests to be sure that our particular case or our particular domain adheres to all the theory that we have. Okay, so that's laziness and ignorance. Laziness is about listing everything that you know or could know or is possible about a domain, and ignorance is about knowing everything about the domain in the first place and running all the tests to check to make sure that what you know about this part of the domain jives with what you know generally, or vice versa. That's the best I can explain it. I'm not an expert in this stuff. I'm barely able to eke this stuff out, but that's the gist of it. But in the end, agents, you, me, machines that we build, still need a way of acting, even though we have the thing. Logic is broken by laziness and ignorance. We can't strictly be logical about everything. We still need a way of acting. Absolute certainty is impossible. So it comes down to importance. So you have to prioritize. It comes down to likelihood. So you have to talk about probabilities. We'll get to that in a second. And then we have to talk about degrees of success. You can't say, either I'm going to do it or I'm not. It's like some things are better. Some outcomes are better than others. Okay. That's quantifying uncertainty, chapter 12. And that's not even one of the big chapters, but I'm going to go through. Chapter 13 is one of the big ones. Remember, we're in the uncertainty section here. This is the big one. Chapter 13 is about probabilistic reasoning, i.e. Bayesian networks. For reasoning with Bayesian networks are for reasoning with uncertainty by representing causal independence and causal conditional independence. When we talk about the causal relationships between things, if we strictly if we want to simplify it from the impossible interaction of everything all the time, affecting everything else all the time, we have to simplify causality using independence and conditional independence. And these relationships, if we simplify using Bayesian networks, these relationships, if we simplify these relationships, then we can simplify our probabilistic representations of the world. That chapter 13 is all about about doing that using Bayesian networks, Bayes nets. Okay, chapter 14, probabilistic reasoning over time. So we just talked about reasoning probabilistically. We talked about quantifying uncertainty before that. What about doing it over time? Comprehending the past, the present, and the future. We've talked about this on Retraice as well. The only, in a sense, the past is unknown in the same way that the future is unknown. This is the arrow of time and all this. You can get into all the philosophy of all this stuff. Well, they're dealing with it from an engineering standpoint. So belief state plus, this is one way of thinking of it. Belief state plus transition model yields prediction. Okay, so if you have a belief state about what is the world now, how does it transition to new things, you can make a prediction about the world. They talk about that. This is in chapter 14, but it also harkens back to chapters 4, 7, and 11. Also, percepts and a sensor model yield an updated belief state. So the belief state changes if you have percepts. Your percept history gets some more stuff on the tail end of it, and then you have a model of your sensors and how they relate to the world. Probability theory. If you add probability theory to that, to belief state and transition models yielding predictions, and then percepts and sensor models yielding updated belief states. I know this is a lot to take on. It's a lot to say. If you add probability theory to that, then you switch from talking about possible worlds to probable worlds. That's a breakthrough. If speaking strictly logically about the world is untenable, it's not, because there's so many details. And our knowledge is always so incomplete. This is like the first thing I read when we started Retraice. Retraice 1 was Russell talking about how imperfect and partial knowledge is. If you use probability theory, which is the quantification of uncertainty, if you add that to what we already have in our system, which, belief states, transition models, percepts, sensor models. If you add probability theory to that, you switch from talking about possible worlds that you're representing in your agent to probable worlds. So you stop talking about, well, it's possible that there's a pink zebra sitting right behind me, now and 5 minutes from now. It's possible. I mean, I can't be everywhere at once. People walk around and they do things, and sometimes they get zebras and they involve zebras and they have paint. Who knows what people could do? But it's so stupid to talk about it because it's not probable. Now we have an engineering way of dealing with the world in a probabilistic way. That's chapter 14, probabilistic reasoning over time. Chapter 15, we only have 4 more chapters, 15, 16, 17, and 18. They're not all going to take up as much space because those early ones really establish the difficulty of uncertainty. Okay, chapter 15, probabilistic programming. We're talking about universal formal languages to represent any computable probability model, and they come with algorithms. They're really universal, like they describe them as being universal in the same way that a Turing machine is universal. That's all technical stuff. No time for that right now. But it's about using formal logic and traditional programming languages to represent probabilistic information. What kinds of what formal languages are we using to represent probabilistic information? And they use formal logic and then traditional programming languages. That's chapter 15. Chapter 16, making simple decisions. This is about agents getting what they want in an uncertain world, often on average. Not every single time. No agent is ever going to be able to do that. But we're making simple decisions in an uncertain world. We're talking about beliefs and desires. We're talking about utility theory and utility functions, decision networks, the value of information, which is very close to the price of information, which we've talked about in the context of strategic intelligence and Major Murphy, Jacques Vallée's Major Murphy. The price of information is very, very important in the world. But this chapter 16 is about simple decisions. We're talking about one-off episodic decisions. Like, you're in this situation, this is what you know, and these are your priorities. Make a decision. Great. Chapter 17 is about complex decisions. These are chains of decisions. So you don't just make your decision today. You know you're going to have another one to make tomorrow. That makes things much more complicated. It's about what to do today, given decisions to be made tomorrow. Sequential decision problems is another way of thinking about it. And that the agent's utility, i.e., like how much you prefer something or how much you care about an outcome, depends on a sequence of decisions in a stochastic or partially observable environment. By stochastic environment, we mean explicitly probabilistic, or that's how they use the term. You can use it other ways, but when you hear stochastic environment, think we're talking about explicit probabilities in this environment. And then we're also talking about partially observable environments when we're making complex sequential decisions. That's chapter 17. Finally, chapter 18, making okay time. This is the other big one, okay, along with chapter 13, multi-agent decision making. Multi-agent decision. This is the real world, man. You're up against good guys and bad guys. You're up against bad guys. You're hopefully with good guys. If you're up against the good guys, then you are the bad guys. Well, whatever, pick your team and we'll fight it out. Good guys are going to win, I'll tell you right now. Multi-Asian? Well, yeah, there are lots of Asians involved in multi-agent decision making, I'm sure. When there's more than one agent in the environment, you got to think differently. They become part of the environment, but agents are not like other things in the environment. These are not objects and relations in the traditional sense. You have to model their belief state. You have to model their transition model. You have to model their percept and sensor model, and you have to model all that in your knowledge representation and your model of the world in a way that you don't have to do with an apple or a block of wood or the wind. You don't have to deal with any of these more complex things that agents have inside them. The nature of such environments with other agents in them. That's one of the major themes, and the strategies for problem solving. These things depend on the relationships. That's the key element here in chapter 18. What makes the difference is the relationships between the agents. We can talk about non-cooperative, you against me, us against you all, or cooperative, us, you all. Those are cooperative relationships, and it's all about game theory and the findings of game theory, and at the tail end of it, they start talking about collective decision making. So yeah, that's it. So those are the two sections, thinking and uncertainty, of AIMA4e. We're talking about pages like 200 to 650, roughly. Again, the book's about 1,000 pages long. Tomorrow, we're going to talk about learning. That's section 5. Interacting, which is section 6. Think robotics and vision. And then section 7. A couple of quick concluding chapters, bringing it all together. That's it. PDFs, the references will be in the PDF notes. Retraice.com, RETRAICE.com. This is Retraice segment number 58. Tomorrow, same time, 11 p.m. Eastern, 8 p.m. Pacific, and all the other times. Signing off.